7.3, number 27, the region of the first quadrant, bounded above by the line y equals square root of 2, below by the curve secant x tangent x, and on the left side by the y-axis, and it's going around y equals square root of 2. So I did graph these. Maybe I'll zoom in a little bit. So this is the region right here that we're going, that's the area, and we're revolving it around y equals square root of 2. So and this is secant x, tangent x. All right, so what technique should I use? Disc, washer, shell, or cross section? Disc is a good choice. Yes, thank you. So it's disc because it's solid. You can see that we're revolving it around y equals square root of 2, so it's going to create kind of like a, I don't know, kind of a bullet sort of shape. Okay, so disc method is always just integral pi r squared. Pi r squared, and it's a horizontal axis of revolution, so we're integrating with respect to x. So we need to figure out from here to here will be our boundaries of integration. Well, the problem said to the right of the y-axis, so we know it's starting at 0. We need to find out that boundary by finding the intersection point. So I'm going to second calculate intersection, first curve, second curve, and I get 0.785. All right, so 0 to 0.785. Now we just have to figure out what our radius is. This is my radius of our cross section. So my radius is this. Well, this whole distance, this distance is y. And another way to represent that, y is always the distance from the x-axis up of anything. So it's actually, this is always going to be square root of 2 here, actually. Square root of 2. So y is equal to the square root of 2. And then this distance is y, because that's variable. So you could describe this radius as the square root of 2 minus y. Square root of 2 minus y is the radius. If I plug that in, it's a problem because my integral is in terms of x. So we have to represent y a different way. Well, how is y defined? Y is equal to the secant x tangent x. So this radius would be the square root of 2 minus secant x tangent x. We can plug that in, and we have our integral set up. Then I would just plug it into the calculator and check answers in the back of the book.